In unsupervised learning, you don't give any answers to the machine. You just want the machine to put them in different categories. So for example, you're giving 1,000 or 10,000 pictures of dogs and cats, but you're not saying which one is a dog and which one is a cat. The machine have to compare these two with each other and come up with different groups. It might come up depending on your criteria and what you define. Machine will come up and say, oh, okay, I came up with 2 categories. Sometimes it might not necessarily be exact dogs and cats that be identified in supervised, and it might not even be 2 categories. It might come up with more categories or less categories. It all depends on what you define. Let me explain how. For example, you want to group students in a school. You can group them based on classes, right? So like for example, you have 100 students and you have 100 students and you have 4 classes. So right now, when you want to group these students, you have 25 in each one of these 4 classes. And then you're going to add another feature, and that is going to be the gender of the students. Then each one of these students are going to belong to a class and are going to have a gender. You're reducing the number of data that is representing each one of these groups. The more dimensions that we are adding to our data set, the more these points, these data are becoming more and more separate, and we have less and less sample to be able to measure. You're talking about the students in a classroom. The age of the student, the height of the student, the mark that the student gets, each one of these are a dimension that is related to that specific student. And then the more feature that you're adding, the more you're separating these points from each other. So how? Then I don't want that much dimension. I'm going to take the dimensions down. But imagine you have few data. There are in 2-dimensional worlds, so they have X and Y. So you're gonna project that in 1 dimension. So this way you're losing some information. There are 2 points in the 2-dimensional world that are far away from each other in 2 dimensions, but then you project it in 1 dimension and they become very close to each other. So you end up saying, oh, guess what? These 2 data points are very close, but in reality, in the 2D world, these two points are far away from each other. But since you reduce the dimension, you're not able to see that, okay? So this is why they call it curse of dimensionality, because we have problem with it and we have problem without it. One of the ways to reduce the dimensions without losing that much information is to use PCA. So how does PCA preserve information? So you have these data points and you cannot change the relationship between these data points. So what are you gonna do? Well, you can't move the axis. You can move the axis in a position that it will preserve the most amount of information. Instead of just removing the y-axis and just keep the x-axis, I'm going to move my x-axis a little bit to see in which position I'm going to preserve the most amount of information. That is going to be my principal component axis. And then the second principal component axis is going to be a right angle to the first one. So as you can see, each one of these principal components are going to be the right angle to the other principal components that you have. So they don't exactly display a feature, but what they do is they change the angle based on all the features that you have. They will, in a space, they're going to change their angle in a way that will preserve the most amount of information about your sample. We'll say the first principal component is going to save 80% of the information, and the second one is going to preserve And the second principal component is going to preserve 12% of this information. So you already have 92% of the information that you need from your samples. So you can kind of, depending on how accurate you want your machine to be, you can get rid of the rest of the principal components since you already have 92% of the information covered. So imagine I have a piece of paper. You don't have to imagine, I actually have. So I have a piece of paper. This is a square. We can see it in two dimensions. We can very clearly see it in two-dimensional world. Okay? And then I'm going to fold this paper. This is still a two-dimensional shape. It's not a cube. It is still a square or rectangle. It doesn't matter. I'm going to fold it. It will give the impression that, this is a three-dimensional data set. But it is not. It is two-dimension, and I just fold it. I made it more complicated by folding it, and it does give an illusion that it is three-dimension, but it is, we can actually unfold it, and it's going to be two-dimension. So in this case, you can use manifold and unfold this two-dimensional data set. Swiss roll is one of these data sets that shows a spiral that is actually a two-dimensional data set, but it is folded in three-dimensional world. If you want to look at it from lower dimension, all these points are going to be inside of each other. And when you're looking at it from two-dimensional world, you don't see any pattern. You can't recognize any pattern. But imagine if you're using manifold and you're gonna unfold this Swiss roll, then you're gonna see the pattern. Imagine I have one-dimensional data set. In this one-dimensional data set, what I mean by one-dimensional data set is just that I have one feature. So I have few X and O's which are in this one line, okay, on this one feature. If I have X's on one side of my axis and I have O's on the other side of the axis, I can very easily just draw a line in between and separate them. But what if there is a pattern, but I cannot have a line to separate these two from each other? I can still see the pattern, but this pattern is not separable in the dimension that I am at right now. So what I mean is that imagine I have X's on one side and I have X's on the other side and I have O's in the middle. You see, I still see the pattern. O's are in the middle, X's are on the side, but this is not separable in the dimensions that I am at. But imagine if I push and I bend this dimension in this form, right? All of the O's are going to be on top here. All of the X's are going to be on the bottom. So now I can draw a line, and on top of my line is going to be all of my O's, and at the bottom is going to be all of my X's. So what is that bend? What did I do? How do I bend that data, that one-dimensional data, one-feature data? How did I bend it? I took it to another dimension. How do we add dimension in data science and AI? We add a new feature. I have to have another axis, but what is gonna be that other axis? I need to be able to bend the line. How do we bend the line? Exponent. So if you take your x to the power of 2, and when you draw it, for example, you have your x here is 1, and then 1 to the power of 1 is going to be 1. So then you have your x at 2, that is going to be 4. And when you draw the line using this new feature that you add to your data set, you are bending the line. And then why is it useful to bend the line? Because now I can find a line that separates O's and X from each other. But again, as we talked about in terms of dimensionality, it's not always a good idea to use polynomials, because every time that you're using a polynomials, when I bent a one-dimensional data set in a two-dimensional data set, I added a complexity to my data set, because right now my one-dimensional data set is two-dimensional. It has the illusion that it is two-dimensional. So what polynomial does is adding more features to your data set. We don't necessarily always need that. There is a way to deal with this, and that is called the kernel trick. So what is a kernel trick? It's going to calculate and tell us the relationship between our data point if we were using a polynomial and we were pushing our data to the higher dimension. It is not actually doing it. It is not pushing our data to the other dimension, and it's not causing complexity to our data set, but it will tell us if you were to push your data set to the next dimension, this is going to be the situations of your data, and this is how they're going to be separated. Imagine you want to figure out how long is it gonna take for a ball to reach the ground if you drop it from, imagine, 10 meter, right? So for the calculation of this time, you can either actually get a ball, go to the height of 10 meter, drop the ball, and calculate how long it takes until the ball reaches the ground, okay? And another way is to use the gravity formula. If you actually use the polynomial in your data set, take your data set to the next dimension, and then do the calculation, that is when you are going and you're getting a ball, going to the 10 meter and drop the ball, and then calculate how long it took. But then if you're using the formula, like the gravity formula, that is the kernel trick. Okay, now we're going to talk about RBF kernels. We already talked about kernel trick, and we already talked about curse of dimensionality. In curse of dimensionality, we talked about how data points are going to be more and more separated as we add more features or more dimension to our data set. So now we're going to talk about RBF kernels. RBF kernels are mostly used for non-linear data set that have very complex relationship with each other, or generally complex relationships. RBF kernel can be used for anything, but since they are expensive, as in you have to use so much memory, the processing time is high, you normally don't use RBF, even though they are very powerful. RBF is one of the most powerful kernels, but you always want to choose a kernel that is more suitable for your actual problem. The way that RBF operates is that it's actually very similar to Big Bang Theory. Not the movie, but the actual Big Bang Theory. So the data set, when you have this complex data set that is tangled together, you're applying RBF kernel. So what RBF kernel does is take your data set to infinite dimensions. As we talked about in Curse of Dimensionality, when you're taking your data set to a very high dimension, what happens is your data starts separating and become more sparse. There's going to be more distance between your data. So in a sense, if you're using dimensions correctly, this is good for your data set because you're basically untangling and making more linear relationship. And that, okay, if I take my data set to infinite dimension, then the space between my data set, the space between my data points are going to be infinite. But that is not correct, because at one point your data is going to be, okay, I am like the rest of the dimensions that you're adding right now, it's not relevant. So it's not going to, they are going to separate to a certain point, but they're not going to separate more than that. The dimension, the space is still expanding, okay? But your data set, after it's separated to the certain amount and then continuing to expand dimensions, doesn't have any effect on it anymore. They're going to travel into this expanding space together. RBF kernel is localized. So it look at localized places. So it will locate your data set wherever it is in this infinite dimension, and it just focuses on your data set. So now that we reach the maximum space between our data points, it comes and it tries to measure and see the similarity between these points. Imagine it's like circles that you are creating around every data set, and then it will figure out which data points are in that circle and or in that radius. So then it will say, okay, so these two are very similar, they can't be in the same category. It will give a score of how similar these 2 points are with each other. And then the way it does it is with exponential decay. The more separate your points are getting, the more irrelevant they become. But RDF kernel is not actually taking your dataset to infinity. It is actually measuring the Euclidean distance between 2 points that you have, not in infinite dimension, in the actual dimension that you are at right now. But instead of just saying, okay, these 2 points are close together, so we're going to say that these 2 points are similar. And then these 2 points are far away from each other, so we're going to say that these two are unsimilar. So why is that not going to work? Again, because your data set is not linear. You can't just have a boundary between the similar data and unsimilar data. Instead, you're using exponential decay. Exponential decay doesn't give you a line. It will give you a curve. That is why it's like using the exponential decay is very similar to actually taking your data set to infinity. And then your RBF is asking you for a value which is called gamma. So gamma shows you how fast you want your similarity to be decreased. So basically mean if your gamma is a small number, the area, the radius that's going to be covered in your data set is going to be bigger. So that means more points are going to be in the same group, or more points are going to be considered similar. But the bigger the gamma is, that means that the radius of this gradual circle that you're creating around your data is going to be smaller, and the less data is going to be held in this, is going to be considered similar. One of the ways, and actually I should say one of the easiest way that you can cluster is with k-mean cluster. Like for example, you said I want 10 clusters. Then k-mean is going to take 10 points and put it in different sides of your data set, in the middle or on the side, it doesn't matter. Just randomly put 10 points, and these points are called centroid, distance between each one of the data points and the points that we talked about, which we're going to call it centroid. It's going to measure the distance between them. Each one of these centroids will go through all of the points, and they're going to measure the distance. All of these data points have to be assigned to a centroid. And each one of these data points pick the centroid that is closest to them. If one of the points is close to one centroid, another point is close to another centroid, but these 2 points are very close to each other, it doesn't matter. One of them is going to get picked up by this centroid, and one of them is going to get picked up by the other centroid. I think you can already see the problem in k-mean. So these 2 points that are very close to each other and very clearly most likely have to be in the same cluster are going to be assigned to different clusters, because different centroids, they pick different centroids. Now that each one of these data points is assigned to their own centroid, these centroids are going to move and place themselves in the middle of the points that have picked them up, right? The points are not going to move, the centroids are going to move in the middle. Now imagine, we have points on one side of the data set and the other points are so far away. Those far away points are getting picked up by the centroid that is far away from them, but it is the closest centroid to them. What's going to happen? Those points that are far away are going to drag the centroid, because centroid have to be in the middle of the points that it has picked up. This centroid that has picked up those far away points, it's going to be dragged all the way there. Okay, so when it is dragged all the way there, these points that it picked up initially are going to be far away from it. Okay, and they are going to be close to the other centroid that didn't move that much, right? So after the move, there is going to be a reassignment. Each one of these points, again, look around and find the closest centroid to them and pick that centroid. These points keep going to move around and reassign, move around and reassign until one of these conditions are met. Centroids are not going to move around anymore, or there's no reassignment anymore. It's done. It says, okay, it doesn't matter how many more time you want me to repeat this process, it's going to be the same thing. There's no more reassignment. And another thing is when you have set a number and you say, I want you to move around, for example, 10 times. If you couldn't figure out in 10 times, then just let it go. And these centroids are just chosen randomly. They can either be very close to each other, or they can be so far away from each other, or it can land in the middle of two clusters. But as you can see, there are going to be multiple problems with this. If two centroids are very close to each other, they might separate a cluster, which is clearly one cluster, into two clusters, because one of them is close to certain points, one of them is close to other points, and they are going to separate one cluster in two clusters. Another situation would be that this centroid has landed between two clusters. So now the problem is that it might consider these two clusters as one cluster. It measures this point and say, okay, I'm in the center, so I don't need to move around anymore. But it is actually in the middle of two clusters, and it is considering these two clusters as one. So these are some shortcomings with k-mean. These two problems that we talked about, and the problem similar to this. So as you remember, we talked about initially choosing random points, and sometimes these points were very close to each other, so they could actually separate two clusters. One of the ways that k-mean++ is tackling this problem, first, it will choose the first centroid randomly, and then it's going to measure the distance between this data point and every other data point that is in your data set. And then it's going to choose the one that is farthest away as the second point or second centroid. And then the third one is going to be the farthest away from these two. And just like this, it will come up with all of the centroids that you wanted, or the number of clusters that you asked for. Say is, if you actually know that you're choosing your centroid far away from each other, the chances of you getting distinct cluster is more than just randomly popping up these centroids and some of them be very close to each other. So when we were talking about k-mean, and we are going to talk about other clusters as well, they don't exactly visualize the data set and based on that saying, okay, the cluster is here, cluster is there. The reason that we are actually seeing the cluster is because we are visualizing the data set. But these k-mean, dbScan, and other clustering method, they can actually visualize the data set and see the cluster with their eyes. But what they do, all of these are happening based on math and formula. So this being said, we talked about k-mean, how it can make mistakes and put two clusters together or separate the cluster in two clusters. There are ways that you can improve the result of these clustering. Silhouette de score is one of these ways. Basically what silhouette de score does, it just tells you how close your point is to its own cluster, and also how far away this point is from other clusters. Or the way that they explain it about silhouette de score, the cohesion and separation. So based on this, it will give you a score, and this score is between -1 and +1. The more closer you get to 1, that means that your clusters are more cohesive. That means that that point is closer to the center of your cluster. And then the more you're getting to -1 means that the more farther away your point is from your cluster, and in fact it is so far that it's closer to another cluster. And if you are at 0, your data point is borderline. It's not close to the cluster that it is right now, and it's not close to other clusters either. So it's like whatever. dbScan is a powerful cluster algorithm, and it is mostly used for complicated data sets, but not data sets that are too big, because dbScan have to actually go to every point. Since it has to examine every single point in the data set, then it's not a very good algorithm for large data set. It's good for complicated data set, for the data sets that have multiple dimensions, but it is not very good for larger data set. Let's talk about what dbScan is calculating when it's going through each single point. dbScan generally focuses on where the density of the data is. And all of that, you need to set it yourself. You need to specify how dense do you want each one of the clusters to be. It will ask you for the number of neighboring points, and it will ask you for a radius, which is called epsilon. Then what it does, it goes to every single point. It will draw a circle, or I shouldn't say circle, a sphere, and then it will figure out how many data points are inside of that sphere. It's not done yet. It has another step. Remember, we said dbScan is going to ask us for a number of points as well. So when it is looking around, it is looking for how many neighbors it finds in that sphere around the data point. And then imagine I say, I want you to make sure that inside of that sphere you have 5 neighbors. Okay? And then dbScan looks at it, each one of these points, it will look at it. If they were 5 or more data points inside of the neighborhood, then it will consider it a core point. So that point is going to be assigned as a core point. If it does not have as many neighbors as it's supposed to have, that is going to be a border point. After it came up with the border points and core points, it will start connecting all of these core points together. Okay? All of these core points that are beside each other are going to form a cluster. So as you can see, we don't need to say how many clusters you're supposed to make, and our clusters are not necessarily supposed to be like a block. It can be any shape. It can be a circle. It can be anything. And because it would just look around and see how many core points are beside each other, and it will connect them. And it's not done yet. And it goes and it finds all of the border points, and it will connect it to the actual cluster as well. Okay? But then, so these are the neighboring points, okay? These are the border points that did not have enough neighbors. Some of the neighbors of these points are actually a core point. Another thing that you have to keep in mind is that dbScan is very good at recognizing noise as well. The reason for that is that it's true that it is connecting all of those border points, but then the points that are close to border points are not considered part of the cluster. Why is that? It's like, for example, when you're going to a party or something and they say, okay, you can bring a +1. So you can bring a +1, but your +1 cannot bring a +1. So that's how it is. Each one of these core points have the ability to bring the points that are close to them, that are border, but they are in their neighbor. But these points that are border points and are not core points, they cannot bring their other points with them. Because of that, dbScan is very good at recognizing noise, and it's very good at dealing with complicated data sets. But again, it's true, it's powerful, and all of these stuff, you have to give it correct hyperparameter. Okay, if for example you are making the epsilon, which is the radius of this sphere, too big, then what's going to happen is a lot of noise are going to be part of your cluster. If you're making it too small, it might separate clusters from each other. Hierarchical clustering, one of the easiest way to imagine it, in my opinion actually, is just the classification of living things and non-living thing, and then you're going to be like different type of animals, and you keep going down and it's become more and more separated, and then you have human, and then you have individual humans. Or you can go other way around. For example, from human you're going to homo sapien, going to mammal, and then you go up to living things and things like that. Doesn't matter if you're going from top to bottom or you're going from bottom to top. You're going to create a tree. This tree is called dendrogram in hierarchical clustering. So now keep that example in mind. There are 2 types of hierarchical clustering. The name of them, one of them is agglomerative and the other one is divisive. The agglomerative is bottom to top. So you start from the individual, you go to homo sapiens, and then you go to mammals. And then if you're doing divisive, then you're going from top to bottom. You go from living thing, and then mammals, and then homo sapiens. You have a data set, like imagine 2-dimensional data set. First of all, the very first clusters the very first level of the clusters are going to be each one of the data points individually, and it just keep gradually increased. It will gradually increase every single layer. They are looking for another data point that is closest to them, and then this will create the clusters. And the biggest cluster have all of these clusters under them. And then hierarchical clustering, you always have to remember, it either starts from one cluster and ends up with the number of all data points, or it starts with the data points and eventually will get to one cluster. So you always have to know that the top layer of your hierarchical clustering is going to be only one cluster, and then when you're coming to the bottom, the width of it is going to be the number of your data points. So depending on how many clusters you want to make from this data set, you can specify a height and then cut it from that height. What I mean, when you're looking at the biology example, if we want only two categories, we are cutting them from the part that says if it's a living thing or if it's not a living thing. So then you are coming to, you have two clusters from this whole data set. You can classify easier, or you go, I don't know, in dinosaurs or something like that. So now we are going through different types of clustering, but very important to look at what type of distance we have that we are using for these clustering. So how do we decide that some points are closer to each other or more similar to each other and some points are far away from each other? And why is that important? Imagine you are like a regular person. For example, when you're going to the kitchen and you want to cook, you don't cook with shovels and axes. You don't cut vegetables with axes. You cut vegetables with knife. So this is the more obvious part of it. So there are some data sets that just make sense to go with certain tools in AI for them than the other. But sometimes you're becoming more and more expert in the field, and your problems are becoming more granular. You will use more professional tools. Like for example, if you're a chef, your choice is not going to be between an axe or a knife, but like for each type of food, you're going to use a different type of knife. There are multiple types of distances that you can use to measure the similarity and differences. Each one of them works best with their own, each one of them invented based on a problem, based on a use case, based on a data set. So sometimes in certain situations, some of them can be interchangeably used, but then sometimes you need more precision and you cannot do that. And for tonight, I'm going to talk about Manhattan, Euclidean, and cosine distances, and then in the future videos, I'm going to talk about the rest of them. Euclidean, as we talked about, is the most straightforward distance that you can measure between 2 points. It's just the shortest distance that connects point A to point B. And then it's the same as Pythagorean theorem that we know about it. It just measures the line that is connecting point A and point B to each other. And then we have Manhattan. It's not the shortest distance, but it is just, for example, if you have an X and a Y and it connects these two lines together, you will add the lengths of X and add the lengths of Y together, and that is going to be the Manhattan distance. From here, we can understand that the Euclidean distance should be shorter than Manhattan distance. And then you would think, well, why do we want to do that? So for example, when you want to get a direction from one point to another point, you don't want to know what is the shortest line that can connect these 2 points together. So that is going to be useless. For example, these 2 points might be very close together, like the shortest line that is going to add these 2 points together is going to be very short, and you would say, okay, well, from here to there, it's just half a kilometer. But you actually don't have any straight street or any line that you can directly go to that point. You actually have to go all the way across from all the buildings and then go to the other points. If your data set is a data set that a certain weight is very important, like for example, what are the chances that someone graduate from school? For example, you have, I don't know, the height of the student, you have the height of the student, you have the hours that the person studied, you have the age of the student, you have so many of these variables. Okay, some of these variables are more important, some of these features are more important than other features. Okay, so for example, the height of the student is not that much relevant to the person graduating than the time that they spend studying. Cosine similarity is not something that you want to go for, because cosine similarity is one of those distances that disregard of the weight of each one of these data points, and it goes with the direction. Cosine similarity is used for similarity between documents, like plagiarism detection and things like that. If I want to give you a very simple example, the person says this is very good, and then the other person wants to say, oh, I said something different. So what they do is they're going to say this is very, 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 very good. And then If you're looking at the distance that's going to measure, that's going to give value to each one of these data points, these two are not going to be similar. But when you're using something like cosine similarity, it does make the weight more, so the vector is going to be longer, but it is pointing at the same direction. If it is vary, it is vary. If it is good, it is good. And then it's going to measure, and then the more similar that they are, the closer the number is going to be to 1, because both of the vectors are going to point at one direction. Sometimes it is not feasible to only use Euclidean distance or only use Manhattan distance to reach your destination, because the goal is here to measure the distance between the start points and the destination. So all the way to the destination, you want to measure this distance. An example for that would be, for example, when you want to travel from Toronto to Vancouver. You're not going to directly go from this point to that point. You can't teleport. You can't get to the airplane from your home. What you have to do is you have to actually drive to the airport. And it is true that we are living in three-dimensional world, but because of gravity, you cannot travel in the z dimension. You're mainly traveling in x and y dimension. And even then, you cannot go through the obstacles that are between you till you reach the airport, because there are houses, there are streets, you're supposed to go a certain path. So you cannot do even Euclidean distance in two-dimensional world. So you have to use the Manhattan. So you use the Manhattan, you reach to airport, and then from there you're using, we're gonna just simplify this, you're using the Euclidean distance between Toronto to Vancouver, because you're getting into the airplane and you're traveling to Vancouver. Euclidean itself wasn't able to take you to the destination, and also Manhattan itself wasn't able to take you to the destination. It was a mixture of these two that took you to your destination. When we're doing something like that, our calculation is going to be a little bit different, and it is called Minkowski distance. The whole point of the distances that are grouped under Minkowski is that they're going to measure the distance until the destination, from the start point to the destination. Chebyshev concept is a little bit different. First, let me talk about the use cases. Imagine you're playing chess. You can't do all of the moves that you want to make in one go. You have to make a move and then wait for the other person to make a move. For example, imagine if your king is at e4 and you want it to be at e6. You cannot do it in one move, because king, as you know, only can move one square at a time. The whole point is that in Chebyshev, you don't necessarily reach your destination. You're just making the biggest move, biggest step that you are capable of making in your turn in order to reach your destination. So Jacquard is very similar to cosine in some aspect. In some aspect, it's completely different. So both Jacquard and cosine similarity tries to figure out how two sets of data are similar to each other. And we already talked about cosine before, so we know that cosine is actually a vector. It doesn't care about the weight. We are looking at the direction. We were talking about the direction. It is very important that our data set be dense, okay? When you have so many zeros for each one of these data points, for the features that are representing each one of these data points, that basically means that your data set is in high dimension. And as we talked before, the higher in dimension that you go, the more sparse your points are going to be. So the chances of them pointing at one direction will become lower and lower. For example, let's talk about the students in a class. If you are trying to only separate the students in the class as in male and female, the females are all going to point at one direction, males are all going to point at one direction. And then you start adding more features to it. You start adding the months that they born, you start adding the amount of time they study per day, you start adding their age and other things like this. When you keep adding these things to your data set, they're not going to be similar anymore. So your vectors start like separating. Okay, so that's what happened with high dimensionality. If you are in high dimension but your data set is dense, you're still going to be fine. If you have so many zeros, you have so many dimensions around you that are zero, okay, but they are still there. And then when one of them is 1, it's going to drastically change the direction between two vectors a lot, because you have so many dimensions for these vectors to spread out. The way that Jacquard calculates is just counts the number of the ones that are similar to the total number. And Jacquard is very good in sparse data, the data that has lots of zeros in it. But when you're having too much data, when your data set is very dense, then it won't be able to tell that much differences, because you might, when you have like 300, 400 word documents, and each one of these words are going to be a feature, chances of these words being similar in two documents is high, but the orientation of these words might be in a way that these two documents are going to be completely different. Each one of these similarities that we talked about, cosine, Jacquard, and Gower, each one of them have some strengths and they have some weaknesses. Cosine does not go through every feature. It takes all of the feature as a whole and says this data point in all of the dimension that it exists, it's pointing this direction. The other data point is pointing this direction. The other data point is pointing this direction. And then if these two data points, if two of these data points are pointing at the same direction in cosine, and they are going to be similar. Okay, and if they are at 90 degrees, that means they are dissimilar, because the cosine for 90 degree is 0, so there's no similarity. If they are at the opposite direction, then they are going to be -1. So pointing at the same direction, and then all of this in between is going to be Gower is still going through each single one of those features. Okay, but what it does is that even if you have different type of features, if you have, for example, some of them are categorical, some of them are ordinal, but then it will transform the data. It will transform the data in order to be able to use it. So it makes all of them of the same kind. So this way, it's going to normalize the whole data set. And Gower, because it has high capability of comparing multiple types of data set with each other, it's not ideal for large data set because it's going to be expensive, as in it will use a lot of memory and a lot of CPU power, because it's going through every single point that you have in your data set, and it's going to compare them with each other, and it has to transform the whole features, like different type of features that you have. So depending on your use case and what you want to do, you have to choose between these. First, let's talk about what is normal distribution. So whenever you're looking at, for example, population, and if the population is large enough, and if it is random, it is generally create a bell curve. When you're thinking about a 10-year-old, what would be the height of a 10-year-old? So imagine, like, for example, 120 centimeters is going to be the height of a 10-year-old. That doesn't mean if somebody's 150 centimeter, they're not going to be a 10-year-old. You might have a taller 10-year-old, or you might have a shorter 10-year-old. The reason you can identify that is because of the normal distribution. Because when you're looking at the kid and then you say, oh, she's taller than what a 10-year-old should look like, or oh, she's shorter than what a 10-year-old should look like. So that just shows that you already have a concept of normal distribution, or the bell curve, in your mind. What K-mean and dbScan was doing, it would say you're either 100% part of this cluster, or you're either 100% not part of this cluster. There's no in between. There's no like multiple cluster for one point and things like that is not happening. They are called hard clustering. Visualize your data set. See how your clusters look like. Now you can see the clusters very clearly, and also they are spherical shape. The best idea is to just go with K. And then if you have like a data structure that are more, it seems like they have more complicated relationship with each other. If you see like patterns that there might be like clusters mixing with each other, and then they are more like spread, like elliptical instead of spherical, your best bet is to use GMM, criminal profiling. It's a very interesting thing. So you can, for example, describe the crime that happened, and where it happened, how it happened, all of these things. And then when you start clustering these into different clusters, and using something powerful like GMM that can capture the normal distribution, and not only that, but also can give scores to each data point, probability of each data point to be part of different clusters. So that is very powerful for a complex task like criminal profiling, which is dealing with human behavior. For example, you describe how the crime scene looks like, and then all of the factors that you have, you will describe all of those factors that you have, and then it will look to see which one of these clusters these will fit in. And then, for example, say it will say the person that you're looking for, he probably it's a male, he will probably weighs this much and will be a muscular person, and it might even go deeper as in say, for example, what type of behavior he might show, if he's a dangerous person or not. You can't say 100% of people who are muscular and over 185 centimeter are serial killer. But then when you're talking about the probabilities and say, okay, this is the crime scene, the chances is that you're looking for this type of person. Imagine that your cluster shows that this person that you're looking for, this criminal that you're looking for, is probably hiding in a washroom in Subway. That does not mean that if you're going to the washrooms in Subway, you're going to find the person that you're looking for. But it's saying that the chances of him being there is more than him being in like a party in Japan. Just to recap, GMM is a clustering technique. It does soft clustering, so that basically means it doesn't assign only to one cluster. It doesn't say it's 100% this cluster or it's not this cluster. So it does soft clustering, and then it is in the form of a normal distribution, which goes hand in hand with probability, because you don't just end it, you don't just cut it off. You're gradually going down, you're gradually decreasing. In this video, I'm going to explain what underfitting and overfitting means in unsupervised learning. In supervised is very similar, but we're going to talk about that later. So when you're talking about unsupervised learning, when you're saying underfitting, that means that your model is very easygoing. It just doesn't care. It has fewer number of clusters, and it says you have 2 legs, you're in the same group. You have 4 legs, you're in the same group. So then it has lower number of clusters. And then when we're talking about overfitting, that means that your model is going through every single details. Like for example, it says, oh, your mole is 2-inch farther away, so I'm not going to put you in the same cluster, you're going to go have another cluster. Both overfitting and underfitting are not good.